Hi, everyone, and welcome to today's session on an optimizing brain for refineries and chemical plants. My name is Allison Buteman. I'm the product marketing manager for Imubit, and I'm joined for today's discussion by Imubit CEO and co-founder Gil Cohen. Gil, you've had an interesting career in mathematics, computers, and entrepreneurship that's led you to here. Can you tell our audience a little bit about how you got to Imubit and how we've come up with this concept of the optimizing brain for their plant?
Yeah, Allison, thank you. So my previous company that I founded was doing new mathematical algorithms inside of silicon chips, like compression and things like that. These things were pretty novel, but they weren't able to change the way that these semiconductors companies operated. And I went on this journey of finding ways to take these novel algorithms and AI and apply them into industries where you can change and transform companies and industries. Deep learning was the focus. I found, after looking at various industrial fields, that continuous process manufacturing and refining is actually the best place to start because refiners have been collecting data for decades. They're just not calling it IoT, and they've been developing mathematical models for decades without calling it machine learning. And so they were open to hearing about these new concepts, and we were fortunate to see good adoption.
So tell us a little bit about what you're seeing in the field and why your customers' challenges are a good match for this type of AI.
Let's look at a couple trends here, starting with the left side of complexity, right? These companies we're helping and the assets that we're trying to optimize are very complicated in various ways. And without getting into all those complexities, I'll say that half of the executives in this industry, they they look at complexity as what's standing between them and their sustainability goals. One of the major challenges, if you continue, is it's really the workforce, the aging workforce, and the fact that new entrants, young generations coming into the workforce are, they're not wanting to come into this industry. They think it's not appealing to them, and they think it's dangerous. And in addition to that, everything is now being impacted by AI, and every company has its own AR strategy, to optimize and transform its business. McKinsey research will say that 3.4x is really the factor between those that use it those that don't. The problem is it is very complicated to find the signal and the noise out there. And I have this joke about AI, right? And it's x plus y divided by 2 used to be called average, and today we call it AI. It really is hard for companies to find what really is that signal and the noise.
So what makes Imubit's AI special and different from the historical averages or the long time math that people have been doing?
What we're doing here at Imubit, we took an approach that is not an incremental approach. It's a very different, it's almost an alien approach coming into the world of incumbents that have been applying various versions of the same concepts for a few decades. We are taking an approach that is more inspired by the brain, and we're calling it an optimizing brain for your plant. Let's think about what that means. Our brains have taken years of information through our senses and years of thought about that information and processing. We're able to solve problems that we couldn't be solved before, new problems that we didn't anticipate every day. Our brains are processing information from our 5 senses. They are fusing that information into one single perception of reality, right? I don't look, smell, and sense something and it creates different versions of it. And that's a very similar thing that we want to do in a plant. You've got one version of reality, one version of molecules through the steel running, and unfortunately, you have various versions of the truth. You have plant economics, process engineering, process control, operations, scheduling, and each group has its own model and its own version of truth and reality, its own opinions and assumptions. We're trying to think how the brain fuses all the different senses. Additionally, the brain is able to our brains are able to apply the knowledge we have on the world and how the world operates, right? Like gravity and friction and momentum, and we compile the information we sense using these principles we know about the world, the first principles of the world. Our brains are also able to handle information that is quite impaired, right, and quite unexpected. Most people are able to read this text here on the right quite phenomenally, and that's because our brains are not just pieces of code that are processing information by fields. We have experience and intuition. Our brains are actually able to handle missing data and corrupt data. Here, the only thing that matters is the first and last letter. Now, however, our brains don't just observe and identify. Our brains are also able to learn how to control the environment, control our bodies, control instruments. These are pretty complicated physical control tasks, and we don't learn them through modeling differential equations. We don't take a child and sit him down and run through a session of nonlinear differential equations and control theory. We let babies learn how to walk and stumble and learn how to run and perform all these control tasks. That's through going through millions and millions of simulations and iterations, just trial and error. And that's how the brain learns how to control and perform very, very complicated tasks.
So, Gil, what does all this sensory fusion and trial and error learning actually mean in the context of a real refinery or chemical plant?
So, as you think more practically, there's a few aspects you really need to consider. Firstly, it's that there's no black box accepted in our industry. You must be able to explain all of the variable relationships that the model that your optimizing brain model has learned, and the rationale behind the decision making. Secondly, safety and cybersecurity are not an afterthought. You must build in these concepts to prevent exposing the plant to any risks, cybersecurity and safety. Lastly, your plant is not just your steel and the molecules running through that steel. Your plant is the people, the folks that I mentioned, these groups, plant economics, process control, process engineering, scheduling, operations, all these people that are working together to optimize those molecules through the steel. And that means that if you want to truly optimize a plant, you must not only optimize the process, but also optimize the process of collaboration between these groups.
So, can you tell us a little bit more about how these groups are working together and how they're using the technology to do that?
Everything we're talking about here is actually something that we have been working on for a few years and have been proven. We've been proving this sort of solution with some of the largest, most prominent energy companies in the world. Here's an example of a problem that we're tackling, a problem that is quite complicated to solve, especially in closed loop. It's a refining complex that includes hydrocracker and an FCC, a gas oil hydrotreater in the front end, and a cat gas hydrotreater in the back end. It's disturbed by your feed composition, your sulfur, nitrogen in the feed, hydrogen availability, your cocoa rate and severity, your catalyst activity, ambient conditions. It's constrained by your product prices, environmental emissions constraints, inventory, and the decisions that you need to make for the teams that are working together to optimize this complex. They vary from how you cut your VGO between your hydrocracker and your FCC, and how you choose the conversion of your hydrocracker given feed quality and product economics, trading off your gas oil hydrotreater and your cat gas hydrotreater in terms of your severity, the hydrogen balance, the octane loss, how you're thinking of your FCC conversion and feed trade-offs given the different prices of the products. It is actually pretty difficult to keep this thing close to its optimal operation at every given point in time. Now, if you want to optimize such a problem, the way we start is really by building one single model of reality that all the different groups can use and see the plant through. We call this evidence-based collaboration. That's opposed to opinion-based collaboration, where everybody brings their own models and their own assumptions, and we try to glue those together. And so to do that, we start with a data-driven model. It's a neural network, a deep learning neural network with hundreds of millions of nodes and hundreds of layers, actually. And we take year or 2 years or more of historical data, process data and lab data, and we train that model and build a dynamic nonlinear representation of the plant, of the process. What I mean by that is that we capture the relationships in various regimes, right? If you take that FCC example, you take the conversion and yield, and you look at that relationship, understanding that it changes with feed composition. So that's what I mean by the nonlinearity. It means the relationship changes. And then, so think of this as a real elaborate model of your plant that is based on your, on your historical data. Then what you do is we realize that historical data can always, in many cases, be wrong. Mass balance can be corrupted by bad flow meters, right? And so you want to compensate for that before you train the model, so that your model does learn to respect mass balance, for example. However, one of the key things about models is that they're always wrong, right? And just like our brain encounters unexpected information, unexpected data and input. So it's the same thing. Every model will always be wrong, and it is inevitable. It's a fact. It's heat exchangers that are fouling. It's catalyst changes, catalyst being added, catalyst being deactivated in various ways. One of the most prominent unobserved sort of inputs to these systems is the composition of feed, right? This is something that is seldom analyzed on an ongoing basis, on an online basis. But interestingly, if you take your operator, it's been there 30 years, your best operator on a conversion unit, they know how to operate that unit, even though they don't have an accurate analysis readily available, right? Online analysis of the composition. They're able to sense what the feed is, right? The feed composition is really based on patterns and temperatures, pressures, flows throughout the unit and downstream and upstream. And they make decisions to accommodate for that, to drive the unit in the right direction in light of those changes. And so if we look at where we are now, right, what did we say? We said we built a model. We built a model of the plant based on data, very high dimensional nonlinear model, dynamic model. We put first principles to it, and we know that it's wrong, right? But how do we go about controlling? How do we go about closed loop optimizing? That's the hard part. What you realize is that traditional approaches cannot really work. If you take a solver and try to apply a solver on such a nonlinear model, you can think of the model as like hills and valleys, like this scheme over here. That's a problem, because what is a solver? What's really a solver? A solver is basically an algorithm that takes the current state of the process and fits it to a model, and then tries to really understand through the model where is the best optimal next step to go to. Problem is, where your model is wrong, your next step is going to be wrong too. And the more nonlinear, high dimensional the model, the further it can take you from your optimum. Right, and that's the problem with a solver. It doesn't see the big picture. It just slips in those cracks, and therefore you need a completely different approach. And this is where some of the special novelty here that we have at Imubit. You need a completely different approach to do this. And we revert to that brain of the operator. How does the operator know how to make those decisions? They know how to make those decisions because of the intuition and the experience they've built over that time. And that's what we want to do. We want to build a solution here that is able to use historical data and build intuition and experience just like a human is able to. There's a field in machine learning that does this. It's called reinforcement learning. Reinforcement learning is the field of taking a neural network and allowing it to learn how to optimize and control complicated processes through experience and intuition. This, by the way, is how self-driving cars are being designed. They're not programmed. It's too complicated. There's neural networks that are able to learn through millions of collective miles how to drive a car. And so what we're doing is we take the model that we just discussed, and we're able to analyze it and understand what the model has learned. And after we do that, then we're able to apply deep reinforcement learning. This is this middle neural network over here. We're able to allow it to learn through trial and error, through millions of trial and error iterations, how to control and optimize the plant based on constraints and objectives. We take yields, we define objective functions, and we take the yields, we apply prices to those yields and feeds, and then we apply constraints. And we don't have to program how it's going to control. We just tell it what is good and what we want it to do, not how to do it. And then we just let it try. And it makes mistakes, it violates constraints, and it doesn't optimize, and we penalize it for that. And then we reward it for correctly optimizing. And we do this at a random time in history with randomized constraints and objective and prices. And after that, we do it again. We tweak the neural network and do it again and again. And we do it millions of times. Every iteration like this takes a few hours. So imagine that you're building a neural network that has the ability to basically hundreds or essentially thousands of years of equivalent experience. It all happens in the cloud. There's nothing intrusive going on here. It takes about a night in the cloud. And then after we've trained this neural network and we've analyzed it and tested it, I can get into how, then only then we're able to deploy it on premise for closed loop control. And then we allow it to write set points to PIDs and DCS or to external targets in advanced process control and things like that.
So Gil, you're throwing around words like neural network and reinforcement learning. And this is an industry that's traditionally used to things that are like what you see is what you get. So how do you get them to adopt and welcome this black box, if you will, style of mathematics?
Over the years, we've been asked these questions of how can I see what the models learn, right? What are their relationships? And if you think of nonlinear relationships, they're not easy to visualize, especially in high dimension. And so what it means, nonlinearity means that the relationship between a pair of variables changes, right, with respect to the process. So the gain changes. And so what we do is we built these tools and capabilities to visualize the distribution of those gains, how they change in various conditions. And then we're able to allow the engineers to explore those, right, and to and understand how the model behaves in various conditions, and how the nonlinearity really comes into play. After the engineers have analyzed the model and feel good about it, all in the cloud, as you said, they need to feel that level of safety. And the way we do this is only after it's analyzed, we then download the model and we install it under the firewall in an on-premise application where we have an operator interface that also helps explain to the operators what the model is doing and where is it going, what's the trajectory, and give them full control of bound and speed of movement and things like that.
So you talked about optimizing collaboration, and you've talked about a bit about the technology. You talked about closed loop. Can you tell us, are there any applications of this technology beyond just the actual control of the plant?
When you think about optimizing the way these people collaborate, the way these groups collaborate, so what we've done is we've taken the models, both the model and the optimizer, and we built applications that allow all of these different engineers to play with these models and learn how to simulate them and run what-if analyses. And it takes literally 15 minutes to train people to do this. We've seen people use this in various ways. We've seen people use this for operator training, for handling conflicting constraints. We've seen production planners that are using this as a what-if analysis tool, where they just want to run scenarios in the cloud, change prices, change conditions, see what the models want to do. We have people that are using the models, using the vectors to feed them into LP models. And so we're working continuously on catering to all these different groups and finding ways of open loop value above the closed loop application.
So if you implement one of these closed loop applications and it starts delivering, how do you make sure that that company continues to innovate and continues to find new ways to capture value from this type of technology over time?
That's a good question, because technology and product alone are not going to cut it. Not in this industry. You can't just throw software over the fence. It's a really good question. And what we're doing is we're thinking about this from the lens of domain expertise. We're building these domain expertise, and we understand that this kind of solution requires never-ending change management and training of the people and strategic partnerships with the right disciplines at the site. That means things like proactively monitoring the application and supporting operators and telling them that something's going to go wrong before it does, before, so they don't need to call you, you call them. It also means that you are, value assessment. Value assessment is tricky. It's tricky. People traditionally do an audit after the project and that's it. And we have teams of folks that were planners, economists, and sites, and they are working with our customers, and on an ongoing basis, on a monthly basis, they come together and analyze the value. So you can't solve this only with technology. There's a certain layer of people, domain expertise here, that is that's brought into this, essentially forever, not something that goes away after the project is implemented.
And Gil, what does it look like in terms of timeline for one of these projects?
It's usually 3 to 4 months from detail, like kickoff and detailed design to closed loop commissioning.
So 3 to 4 months, that's pretty quick. Can you tell me some examples of how Imubit's actually been put into place in the refining industry?
We have over 70 applications that we've implemented over the years, some of them running over 5 years. We're very proud to work with some of the largest energy companies in the world. 7 of the top 10 US refiners are using our technology, reporting 30 to 50 cents a barrel, typically, and 10, 20% in energy efficiency. And they go on the record, and they speak about what they're seeing. So this is not a concept or an idea. It's actually a solution that is proven in the industry.
So Gil, I see in that middle quote, we've got a comment about true AI. And I'm curious what your take is on how true AI is advantageous over whatever we mean by untrue AI, or what are the other approaches out there, and how is Imubit different?
Yeah, we already talked about AI being ambiguous, and I think there's a lot of approaches that take a model, first principle based model, right, and then just use neural nets or any other method, machine learning method, to fit parameters into that. And that's not something that is groundbreaking or changing. People have been doing that for a very long time, and it still means you are taking assumptions, making human assumptions that are biased by definition, and you are quite generally destroying value by doing that, right? Your data can tell you more if you start with the data. That's what we mean. So starting with a model that is data first, applying the minimal number of assumptions you need to make sure your data is correct and your model does not contradict the envelope of fundamental first principles. But that's where you stop. You let the data do the rest.
Awesome. And for folks that are interested in everything that we talked about today and want to get to know this optimizing brain concept a little bit better, how do they get started?
I think we've got a good start here.
So you can scan the QR code on this slide if you would like to test your SME experience and knowledge against Imubit's optimizing brain. This will give you the chance to interact with the software as well as with the customer success team at Imubit. And spoiler, nobody's beat the AI yet, but maybe you'll be the first one to beat the AI. I want to thank our CEO at Imubit, Gil Cohen, for joining us today, and I hope everyone has a great day.